So I'm going to turn the tape on there. Welcome to Monday. This is your first class. Have you already had 8:30 class? So we have a homework due tonight on composition and inverses, and this one's not really that long, so so this one should be, I think, fairly easy to complete by tonight. And then we really don't have another homework until next Monday. This homework, which we're going to talk about today on trigonometric graphs, so we're finally ready to go back and revisit the graph of trigonometric functions after a long detour there through a sort of advanced topics and functions. So this is not due till Monday, but this is not on the test, which will be a week from Wednesday, right? So there's a test scheduled for April 6th, which is a week from Wednesday. So that test stops with composition and inverses. Now, but that's a lot of material since the last test, because that includes the right triangle trigonometry that was not on test number 1. So I have you can barely see it there, squeezed in on the right hand side here. There's the announcement that the sample test is posted. So if you go to Blackboard, it's there in the usual spot under sample tests. So there it is. And so it's long now because it includes this right triangle trigonometry. So it looks like it's really long, but a lot of that has to do with the fact that there's a lot of drawings of triangles in here. So that takes up a lot of space. And so I don't think the individual problems are as difficult as all that bad. So so again, you want to work through this, right, as much as you can before the test. Now, remember, on here, there will be some problems, right, that have diamonds in them, right? And so these are kind of not really more advanced problems, but maybe problems that you should focus on less than some of the other problems on the sample test, okay? So these are less likely to, problems like those are less likely to be on the test. So you may save those for later when you're working through the sample test if you don't have time. So problems like 10 and 11 and whatever else is marked here with a diamond. I wanted to point out, I noticed on that composition and inverses homework, so here's increasing, decreasing, that takes a lot of space, see, so because there's a lot of graphs, so it's not as long as it looks. I wanted to point out that there's, on the homework, there's not a lot of problems with composition. So like this problem number 21. So you may want to look at the problems that involve composition, like 21 and 22 and 23. You may want to, that page especially, you may want to make sure that you do those problems before the test, because those things are kind of neglected in the homeworks, but they are in the notes. 20 is a good problem too, but I have that one marked as a diamond. So so this page is more important, I think, for the test. Okay. Problem number 19 also there. That's just a straightforward composition problem. So that's a good practice problem also, because in the homework, there's not many problems where you're just composing functions and finding the formula for the composition. Okay, so there's the sample test, right? So so you want to start working on that. So since we really don't have a lot of homeworks between now and the test, right? So you got plenty of time to work on the sample test. So you want to focus your energies on that between now and the test, I think. Okay. Speaking of homeworks now, and that homework that's due tonight, let me open that and ask if you guys have any questions. So I have a question that I'll ask you guys on this very first problem. So this is supposed to be easy, right? Just want to clarify here that you're not making some sort of elementary mistakes. So about inverses. So when it says f has an inverse, then f inverse of x is always the same as 1 over f of x. Is that true or false? Yeah, that's false, right? If you're thinking that f minus 1x there means 1 over f of x, you're treating the minus 1 superscript as an exponent. That's another way we use minus 1 in math notation, right? We use it as an exponent, and that does mean reciprocal. But in this context, in the context of function, that just means the inverse function. And so that's not necessarily, it could be, but it's usually not the same as 1 over f of x, right? So this is false. And then there's this problem, part B there, which again, just true or false. It says if f has an inverse, then f inverse composed with f of x, this is composition, right? Is equal to x. Is that true or false? True, right? Yeah, that's the inverse function property, right? So, and that's really the property that's going to make inverses useful to us when we get around to applying inverses in a couple of lectures here. The fact that when you compose an inverse function and the function itself, just get things simplified to just x, okay? All right, so do y'all have any other specific questions about this homework? I think it's I think it shouldn't be terribly difficult here. Let's look at this problem number 5, since that one seems like that should be an easy one. So it says, assume that f is a one-to-one function, which means it has an inverse. But and remember, not all functions have inverses, right? So, but assume f does have an inverse. And so the first part there is, it says, if f of 9 is equal to 6, then what is f inverse of 6? So they're not giving you a formula for f or a formula for f inverse there also, right? Okay. So, but they're asking you this, question about evaluating these functions, right? So maybe left to wonder, how do I do that, right? If I don't have a formula for f or f inverse, I don't have a graph. But it's just a matter of remembering what the inverse function actually means, right? So how did we initially define inverse functions? Just said to create an inverse of a function, what do you do? Not how do you find its formula or how do you find its graph? Those are also things we practice. But right at the beginning, when we're saying what an inverse function is, how inverses work, you recall just the basic definition of how to create an inverse. It's very simple. You switch x and y, that's right. You flip inputs and outputs, okay? So you just have to keep that in mind in thinking about this problem. So you see, if f of 9 is equal to 6, then in inverse function, you flip the x and the y, okay? So that means f inverse of 6 must be equal to what? 9, right, yeah. Just flip the x and the y, okay? So so that answer is really easy, okay? Although it's, oh, oops, wrong keyboard there. That's really easy, although at first there it looks like it should be confusing, right? And then backwards would be the same, okay? So if f inverse of 5 is equal to -2, then what's f of -2 going to be? 5, right? Yeah, sure, right. See, it's just that easy. So at a very basic level, inverse functions are really easy to understand, okay? The way we create inverses is easy, all right? Now, okay, now it gets a little bit harder now if you want to ask more complicated questions about inverses like in number 6, right? So here they're giving you the formula for f. So f of x is 4x plus 6. So what sort of function is that? If you make a graph, well, yeah, that's linear, right? Okay, it has slope of what there, Ravi? 4, yeah, and crosses the y-axis at 6. So because its slope is 4, right? Okay, you can sort of visualize what that graph is going to look like, right? Because you graph it, you're going to get a straight line. So what is that straight line going to look like, Ravi? Just, yeah, it's just increasing line, right? Okay, it's got a pretty steep slope of 4, so it's going up pretty quickly, and it crosses the y-axis at 6. So it's really going up quickly. So Robbie, would that have an inverse? Yes. Yeah, that's right. So because it's increasing, right? Okay, that graph is increasing. If you were to draw a horizontal line, right, would not cross that line, that graph more than once, right? Okay. In other words, you don't have any repeated y values on that graph, no repeated y values, because it's always increasing. The y values are always going up, right? Okay. So you can't get repeated y values. To get repeated y values, you'd have to have some point where the graph decreases, right? Okay, so you could repeat a y value, but that doesn't happen here. So it does have an inverse, and now they're asking you what is the inverse, right? So what's our game plan there for actually discovering the formula for the inverse? You remember what you do now?
You just
Yeah, so Amanda, so be more specific there for me. So instead of writing f of x, we would write instead what? No, we would write y, right, instead of f of x. So you would write y equals 4x plus 6, and then do what? You just said it, right? Huh? No, you just said it though. So you know it. No, yeah, we have y equals 4x plus 6, and then what do you do with the x and the y? You flip them, right? Okay, yeah. So you flip them, all right? So you would have x equals 4y plus 6, and then do what? Solve for y, right? So you would solve the resulting equation for y, and that would give you the formula for f inverse of x. So it's back to flipping x and y, right? Okay, same thing. So on these problems, like 6, 7, and 8, right? Okay, that's the procedure that you're going to follow, like we practice in class. Now, as we did at the end of class last time, okay, if you're looking for the graph of inverse function, so here we have a function f this is called a piecewise linear function because it consists of 3 pieces, all of which are straight lines, okay? But that's either here nor there for this question. What we want to identify is what the graph of f inverse looks like. And it's the very same idea, right? To create the graph of f inverse, you're going to look at the graph of f and you're going to flip all of the coordinates for all the points, right? You're going to flip the x and the y coordinates for all the points on that graph. Well, you can't do that by hand, right? Because there's a lot of points on that graph. But what's the net effect when you flip all of those coordinates? What effect does that have on the graph? So what ultimately does that do? So geometrically, what does that do to that picture? It flips it, but in what way, Amanda? Yeah, so can you say that in her my notes? Okay, Amanda, what were you saying? A reflection around what though? A mirror image of 45-degree line. That's right. Yeah, there you go. Okay, so it rotates it or reflects it around a 45-degree line. So if you visualize the 45-degree line here, right? Okay, running through that graph. Okay, then when you create the inverse, it's going to rotate that graph around this 45-degree line. Okay, so this part is going to get rotated up here, right? Okay, and I guess this piece would get rotated to the bottom here, right, around that 45-degree line. Which one of these now? So you have to kind of pick it out, right? Which one of these is that rotation? So if you take this and rotate it around a 45-degree, which one there? Say. Emil, you said what? D, which is this one? Yeah, I think that's correct, right? Okay. If you want to sort of nail that down a little bit, you might pick actually some points off of this graph, right? And think about rotating their coordinates and what point, flipping their coordinates, right? At what point you're going to get. So this is the point, what is that, 10, 1, right? Obviously. So if you flip its coordinates, you get what? 1 and 10. Does this have 1 and 10 on it? Yep, there it is right there, right? 1 and 10 is on that picture, right? Okay, or here's the point 5, 0. So if you flip that, you would get what? 0, 5? 0, 5 on here? Ah, yeah, there it is, right? Okay, so that's kind of giving us evidence, right, that Emil's idea there, Emil's eyeballing it there is correct, right? The right answer there is going to be D. So you can, so you have to apply that same logic here to all of these. Well, there's only a couple of them, right? To these two examples, right, where you're trying to think of what the inverse graph looks like. We had a problem like this last time, right? Remember on the sheet, and a couple of problems like this. Let me see if I can find it here. And so, yeah, so we had first decided that these two were not one-to-one functions, right? So these didn't have inverses, so we didn't have to worry about drawing them. But these two were one-to-one functions, so we were trying to draw their inverses. We drew the inverse of this one, and we didn't quite have enough time to draw the inverse of this function. It's this curve right here, right? We were thinking, ooh, if I rotate that around a 45-degree line, there's a 45-degree line. What's that going to look like? Let's see if we can draw that in now, or at least scribble it a little bit, right? So what do y'all think? So if you take this piece, right? Okay, if you take this piece, right? Let's start with the piece that's below the 45-degree line, and we rotate that around the 45-degree line. What's that going to look like when it gets rotated around this piece, right? When we get that rotated around the 45-degree, obviously it's going to be above the 45-degree line, right? Looking like maybe what? Maybe like this? Is that sort of it? I think. Yeah, just think about taking that and drawing its mirror image up here around this. I didn't draw that too great, right? But it'll look something like that. Okay. What about this piece when you rotate it? So that piece there, about rotating that around a 45-degree line, what's that going to look like? You want to try plotting a few points to nail it down? You can always do that. Okay. So let's see what points look like they're on here. What this point looks like what? -2 and this point 1. So that means that on the inverse, you're going to have what? 1 and -2 right there. Okay, so we got that. That's comforting. See, what's this look like? That point, -4 and about what? 1.5. So on the inverse, we would have what? 1.5 and maybe -4 right there. Yeah. Okay. What about this point way over here on the edge? That's almost 2, right? So -8 and almost 2. So here we have almost 2 and -8 right there. So it looks like when we rotate this piece, we get something like this. If I can draw it. Yeah, okay. So you see, it's not always perfectly obvious, right? what the inverse graphs are going to look like. I think we got it there, sort of. Okay. That's why sometimes it's useful to be able to write down the formulas, okay? Because drawing the graphs is not always foolproof, right? Okay, all right. So so much for that. So I think y'all can. I think y'all will be able to finish the homework there, at least on composition and inverses, pretty easily. Well, let me give y'all a recall practice. So this one is kind of straightforward now. All right. So I just want you to show that if you have this function f of x equal 2x minus 5, so that's a linear function. Its slope is 2. The y-intercept is -5. So that linear function is increasing because its slope is 2. So it's going to have an inverse, definitely have an inverse. And my claim is that that inverse is this function g of x, which is x plus 5 over 2. So I'm claiming this function g is really the same as f inverse of x. But I don't want you to try to write down the formula for g using the technique that we were discussing for the homework. All I want you to do there is just show that these two are inverses by composing them. So take the composition of f with g, f composed g of x, and use that to prove to me that, oh, these two functions really are inverses of one another. And if they are inverses of one another, we just answered this question in homework. What happens here when you compose them? You just get left with x, right? So you're just checking to see if I take f composed g of x, do I get x? All right. Well, if don't come up with x, then that means either we've done the composition wrong or they're not inverses, right? Okay, which is a possibility. All right, even though we know that function f had inverse, has an inverse. So try that. Okay, so just do the composition. Don't try to take, y equal 2x plus 5 and flip the variables and solve. All right, that would be another way of discovering g. But here I just want you to do the composition to show that they're inverses. So this is kind of really just a question of, do you remember how to compose two functions? Something that will be on the test, but is not really, there's not enough of that in the homework. So be sure to do those types of problems on the sample test. Okay, John, get started there because I'm going to come around and see what you're doing. You guys at home, do this too. Try composing those and see if you come up with x, right? Okay. We're looking at a homework problem here. So, f of g of x, right? Yeah, so what happens? Gasoline. Yeah. That's what you want, right? If you want it. All right. But yeah. But here, yes. What do you want, right? That makes sense. So what's that composed of? That's really important. That's what's you? No. And okay. Yeah. Yeah, that's supposed to be. Yeah, it's supposed to be x. There's supposed to be inverse. Yes, this is the right one. So what's the time to be? I'm not sure. This is No, the tubes can't. So I think stop. But you, yeah, but that's what you want. Because when you close function X. Usually, now remember, usually with those functions, you won't get just X, right? I'm telling you what you would get, okay? But you won't get just X. No, it's with X. Right. It can be. Right. Oh, great. So that was a good exercise to remind you of. That was a good exercise to remind you of composition. Some of you are still a little bit fuzzy about composition, and as I mentioned, there's not a lot of that in the homework. So be sure to do those on the. If you have trouble remembering that, because I know you've done that in prior math courses. So if you have trouble remembering composition, be sure to do those problems from the sample test. Did I leave that open? I don't know if I left it open or not, but it's basically, as I recall, problems 19 through 23 there on the sample test had to do with composition. Okay. So f composed g of x means f of g of x, right? That's the basic definition of composition. And so then we just start doing the evaluation here. We know what g of x is because we have a formula for g of x, right? That's x plus 5 over 2. So instead of g of x, you can write x plus 5 over 2. And now you take all of this, right, and plug it in for x in the formula for f. So you get 2 times x plus 5 over 2. And don't forget the minus 5 that's part of the formula for f. And now these twos divide out, right? So this works out nicely. You get x plus 5 minus 5, which is x. And that's what we wanted to see to demonstrate that those things are really are inverses of one, right? Okay. Well, now now we're changing topics here completely, sort of completely. It seems like completely, but we're not. But we're going to get back to inverses, okay? Because they play an important role in trigonometry, believe it or not. All right. But for a moment here, we want to talk about graphs of the trig function. So we've looked a little bit at graphs of trig functions, just sine and cosine. So and we know shapes of those curves, right? Okay, but we're going to look at that a little bit more in depth now. So recall that just the basic shapes of the sine and cosine curves. The domain of those sine and cosine functions is going to be all real numbers. So when you graph the sine and cosine function, those curves extend indefinitely to the left and the right. And remember, those curves are oscillating, right? So they're going up and down. They cross over the x-axis many times, and they have many peaks and valleys in them, right? Okay, and but their range, okay, just the portion of the y-axis, right, that is consumed by the sine and cosine curve is just -1 to 1. Okay, so the basic sine curve never goes above 1 or below -1, and same thing for the cosine curve. It never goes above 1 and -1. And then an important fact that we had already noticed about the sine and cosine curves is that these curves are what is called periodic. All right, so that means they oscillate and they repeat. Okay, the curve repeats every 2 pi units. So if you look at so that's what this property is actually stating, kind of mathematical terms. So if you look at the sine curve or the cosine curve, here's their graphs, right? Notice that if you take this piece of the sine curve or the cosine curve from 0 to 2 pi, right, and you just replicate that piece to the right or replicate that piece to the left, you get the entire sine curve, the entire cosine curve, right? Okay, so that's what we say that the period of the sine curve is 2 pi, okay, because this piece of the curve repeats itself every 2 pi units, indefinitely to the right, and then also indefinitely to the left. And same thing for the cosine curve, all right? This a piece of the cosine curve from 0 to 2 pi, if you cut that and duplicate that to the right or to the left, you will get the entire cosine curve.
I want to say thank you to Venus and Serena and the
Someone needs to
family for entrusting
mute their mic for me. Is that you, Mauricio?
That's what I want to do. I want to be an
I'm
ambassador.
going to mute you. Okay. So now, as I already mentioned just a moment ago, because the sine and cosine curve are periodic, right? They have this period of 2 pi units. Then you get lots of x-intercepts, right, for both the sine and the cosine curve, and you also get lots of peaks and valleys. That's local minima and local maxima for the sine and the cosine curve as well. All right. So in fact, for the sine curve, you're going to have an x-intercept at 0, get an x-intercept at 0, and then every pi units after 0, you get another x-intercept. So what this notation means is that if you take 0 and add or subtract on multiples of pi, you will get another x-intercept for the sine curve. So 0 plus 1 pi, or 0 plus 2 pi, or 0 plus 3 pi, etc. Those are all going to be x-intercepts for the sine curve. And you can also subtract as well. So 0 minus pi, in other words, minus pi or minus 2 pi or minus 3 pi, those will all be x-intercepts for the sine curve. The same thing happens for the cosine curve. The x-intercepts for the cosine curve also occur every pi units along the x-axis, but the first one is at pi over 2, not at 0. Remember, the cosine of 0 is 1, okay? And you don't have the first x-intercept for the cosine curve until you get to pi over 2. So if you look at the graph, you can see this very clearly on the graphs of the sine and the cosine curve, right? A sine curve starts at 0, so that's an x-intercept. And then you have another x-intercept every pi units, right? So at pi, it crosses the x-axis again. So sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, and so on and so forth. For the sine curve, however, the first x-intercept is not until pi over 2. Remember, cosine of pi over 2 is 0. And then again, every pi units after that get another x-intercept. The same thing happens for the local minima and local maxima. So for the sine curve, you have your first peak at pi over 2. Remember, sine of pi over 2 is 1, and that's going to be the highest that the sine curve ever gets. And then you get a valley, another local extrema here at pi over 2, pi units away. So pi over 2 plus pi plus another pi brings you back to another peak, right? Plus another pi brings you back to a valley, and so on and so forth. So you get peak and valley points every pi unit along the sine curve, starting at pi over 2. And the same thing happens on the cosine curve. You get peaks or valleys every pi unit, starting at 0, though, for the cosine curve, because cosine of 0 is 1. So you get a peak here at 0, you get a valley here at pi units away, and then another peak at 2 pi, then a valley at 3 pi, and so on and so forth. So you have lots of x-intercepts and lots of peaks and valleys on the sine and cosine curve because they're periodic, right? Okay, they repeat. The curve repeats every 2 pi units. Now, in applications though of a sine and cosine curve, we're not going to be applying just the sine or just the basic sine and cosine curve. Instead, usually what we're applying in applications are transformations of the sine or the cosine curve. Transformations of sine and cosine are called sinusoidal functions. All right. So anytime you apply a transformation to sine or cosine, you get what's called a sinusoidal function. So it's not quite a sine or a cosine curve, but it's close to that, right? It's just a transformation. So remember, what kind of transformations do we have? Y'all just finished your transformation homework, so you should remember this, right? We have what? Stretches and shrinks, right? And what? So we can stretch or we can shrink, right? Or what else can we do? What? Huh? Rotate, right? Yeah, we can rotate around the x and the y axis. So we have rotations, and then what's the other one? Kind of the easiest one. What? Yeah, shifts, right? Okay, so we also have shifts. So we're going to apply those transformations also to the sine and cosine curve, and when you do that, you get again what's called the sinusoidal function. Let's look at some sinusoidal functions now, and because of your knowledge of transformations, you're going to understand what the graphs of these functions look like really easily. Okay, so so we're not going to graph these functions usually by hand. We're going to graph them with either a computer or a calculator. But even without the graph, even without making the graph, you will be able to imagine or understand what the graph is supposed to look like. Okay, so you can describe the graph or visualize it pretty easily without even graphing it. So for instance, let's look at this one. Cosine of x plus 2. What is that going to look like if you were going to describe it? It's going to look something like the cosine function, right? Okay, but what's the difference? It's shifted up 2 units, right? Okay, so this has been a shift, right? And this is a vertical shift. Okay, why is that a vertical shift? Because remember that 2, you could, if you wanted to, move it to the left, and you would have y minus 2, and so you know that's a transformation on the y-axis, right? So that's a shift. In this case, it's up 2 units. So this is just a plain cosine curve with all of its wiggles in it, right? It's just been moved up 2 units. That's all. What about this one? Yeah, that's been rotated. What's it? How's the rotation? Around what? Around the x-axis, right? So we've just taken the sine curve here, and because we put this minus sign in front of it, we've just rotated the sine curve around the x-axis. So that when you rotate the sine curve around the x-axis, of course, it really looks kind of like the sine curve again, right? Okay, it's still got all the wiggles in it, except instead of starting going up, this curve will start by going down, okay, because it's been rotated around the y-axis. I've got graphs of these, so let's actually look at them so we can sort of confirm our suspicions here. And on your homework now, when you're graphing, so you're going to be asked to graph in the homework, but remember, you're not meant to do that by hand. You're meant to do that either with your calculator. If you have a graphing calculator, that's fine, or otherwise you can use Desmos. And remember, I have a link to Desmos at the top of the homework. So you can open Desmos and type in whatever sinusoidal function you're being asked to graph, and you can see it. All right, so here are these examples. So what I've got plotted here is there's cosine of x plus 2. Does that look like the cosine curve just shifted up? I think so, right? Okay. If you take off the 2, So we could here very easily, right, just take off the 2, and you can see what effect that has, right? It just shifts the curve back down. That's the cosine curve, right? Remember, cosine of 0 is 1, right? Okay, then it's going to go down. You can't see it over here, but it's going to go down to -1 at what? Pi, right? Okay, and then comes back up again. So so this is just the cosine curve, except been shifted up. Let's move it back to shifted up there if I can find my plus sign there. All right, yeah, see, notice that just shifted the whole thing up. Let's look at minus sign. So let me turn this one off and turn this one on. So this is just supposed to be the sine curve, except rotated around the x-axis. So you can see that's what's happened, right? Okay, normally the sine curve would start by going up and then come down. Notice this one, because it's been rotated, is going down and then it's coming up. If you take off the minus sign, right, what's going to happen is this is just going to get flipped if we take off the minus sign. Oops, what did I do? Oops, I took off the S. That's bad. I think it knows what capital S is there. So there we go. All right. So there's the usual sine curve, right? Okay. It's over a little bit so we can see it better. There's the usual sine curve, right? Just going up and then coming back down here. So it goes up. What's this? Where does it hit this peak point on the x-axis?
1.
Yeah, that is 1, but where on the x-axis is that, Amanda? Where does it hit that peak? No, but you know it exactly. You're right. It's close to 1.8, but you know it exactly. Pi over 2. It's pi over 2, right? Remember, sine of pi over 2 is 1. Okay, and then it goes back down to 0. What's that? So what's that on the x-axis? Where does it hit 0 again? Not 2 pi. It does hit it at 2 pi, but it hits it before 2 pi. Pi, right? Okay, sine of pi is 0, and then it hits -1 at what? In radians, what would that be? 3 pi over 2, right? Okay, and then it comes back up to 0 at 2 pi, right? That's when it completes one full period there, right? That's one full rotation, right? From 0 to 2 pi. Okay, so when we put the minus sign on it, all of this just gets flipped, right? You see it flipping it. Okay, all of that just gets rotated around the x-axis. What about the next one then? Before we even graph it, we'll turn it on here. What does that do? So 2 cosine x. So what kind of transformation is that going to be? It's a vertical stretch, Evan, you're right. So what's the effect of that then? Times 2, right? So it would double essentially all of the y value. So so normally, right, the cosine curve goes up to 1 and goes down to -1, correct? So, but when you add this multiple of 2, you're going to get a vertical stretch. Okay, and so that's going to stretch it to going up to 2 and down to -2. Okay, so it's going to be taller than before. So see, that's taller than before, right? It looks like the cosine curve, except instead of just going to 1, right, now it goes up to 2 and down to -2. Okay, remember it goes down to -2 at, this is at pi, right? Okay, and then back up to 2 at, this is 2 pi. So what effect does that have? Yeah, vertical shrink, right? Okay, so so how much does it shrink it there, Fernando? By a fact, yeah, shrinks it by a factor of 2. In other words, make that a little more clear. See here, it multiplied everything by 2, so this is going to multiply everything by what? By 0.5, right? So instead of going up to, normally it goes up to 1, right? The sine curve goes up to 1 and goes down to -1. How far up and down is it going to go in this case? Yeah, just 0.5, right? Okay, so it shrinks it there by 1/2, right? And the minus sign, though, is also important. That rotates, okay? So normally the sine curve starts by going up and then coming down. With the minus sign, it's going to go down before it comes back up again. Let's turn that one on. And so you can see it, right? See, it flattens out there, the sine curve, right? It's not going up to 1 and -1, only going up to 1/2. Right there and down to -1/2. And notice now, instead of going up to begin with, now it's going down, right? Okay. So see, y'all understand these curves, right? Pretty easily, just based on your knowledge of transformation. So see, that was a time that we had well invested, because most people have a hard time understanding sinusoidal curves when they first see them. All right, so here's what actually we just discovered in those 4 examples, if we sort of think about what we were looking like, okay? So in general, what we know is that if you multiply sine and cosine by a constant here, right, in front, what you're doing is you're performing a vertical stretch or a vertical shrink, right? Okay, and if the number in front is negative, you'll also have a rotation. This number multiple in front of the sine or the cosine, usually we label that A, because this is called the amplitude of the sinusoidal function. So when you multiply sine and cosine by a coefficient, you're altering what's called the amplitude of the curve. In other words, how far up and how far down that curve is going to go along the y-axis. And the absolute value of this number, the reason we have to put absolute value here, sometimes we can make this negative, right, which will do a rotation. But the absolute value of this coefficient in front of the sine and cosine, that's called the amplitude of the curve. So y'all can describe very easily for me what these curves look like, right? Tell me what their amplitude is also, though. So what is the amplitude of this sinusoidal curve? It's almost the cosine, right? Except we have this coefficient in front, right? So what is the amplitude here? 3, right? Yeah, remember, that's going to be the absolute value of the -3, which is 3. So what's that effect then on the graph? Stretches it, triples it, right? Okay, so it's going to make it 3 times as tall, or 3 times as low, right? Okay, and also because of the minus sign, Amanda, it's going to what? Not shrink, but what does the minus sign do? That rotates. Okay, yeah. So it's going to rotate it around the x-axis. All right. What about this one? Yeah, that one has a very small amplitude, right? Of amplitude of the absolute value here of 0.01, which is 0.01. Yeah, so this graph is really getting shrunk, right? Okay, it's really going to get flattened. So when you graph that one, if you don't sort of enlarge your graphing window, it's going to look like the x-axis, because it's going to be very close to the x-axis, because it's been really flattened along the really flattened vertically, right? Okay, let's look at the graphs here and see what the graphs look like. I think I've got this one in a different example. So there's -3 cosine of x, right? So see, the amplitude now is 3. It's going up to 3 and down to -3, but it's been rotated because of the minus sign. So normally the cosine curve would start at a peak, right, and then come down, but it's been rotated. So it's starting at a valley and coming up instead, right? But what's really important there is not the rotation, but that peak in that valley, right, is at 3 and -3. Let's turn this one off now and turn this one on, and I think we're not going to hardly see anything. Can y'all see anything there? Y'all see what I got when I turned that one on? Notice it put a blue line there along the x-axis, because this is so flat, its amplitude is so small that it looks like a flat line. It looks like the x-axis. So to see this one, you're really going to have to zoom in on it. Wow, I don't even know how. Oh, are we starting to see it there? Just a little bit. There it is coming up, right? Okay, and then eventually here, if we go over far enough, it'll come back down again, right? Okay. So in graphing this curve, you really need to adjust your graphing window. Mainly the y-axis, right? Okay. You only want to graph a little tiny piece of the y-axis because otherwise you're not going to see that curve very well. Okay. All right. So vertical stretches, right? They impact what's called the amplitude of our sinusoidal curve. Now, of course, we also can affect. We also can have horizontal stretches as well, right? Okay. And so to get a horizontal stretch, you know that you'll multiply the x by a constant. So we can also in these sinusoidal curves multiply the x by a constant. So notice that our multiple here is inside of the function, right? Next to the x, not in front of the function. And so that gives us a horizontal shrink or stretch. So what that is going to affect when you have a horizontal shrink or stretch, that's going to affect the period of the graph. All right. Remember, normally a sine or a cosine curve repeats every how many units along the x-axis? Every 2 pi units. But if you shrink it or stretch it, you're going to change how often it repeats along the x-axis, right? If you shrink it, it's going to be repeating much more frequently, or if you stretch it, it's going to be repeating less frequently. It's easy to compute the period, all right? So how frequently a sinusoidal curves repeat. All you have to do is take this multiple of the x and divide that into 2 pi, and then you can calculate what the new period is going to be. Okay, so how frequently the curve is going to oscillate, okay? And of course, the amplitude we already mentioned, right, is the coefficient of this, is the coefficient in front, right, of the sine or the cosine function. So, in this example, we have both. We can have both vertical stretches, right, and also horizontal stretches as well. All right, let's take a look at some examples there. Oh, by the way, if Cengage is ever down and can't log on for some reason, if WebAssign is ever down, you can go to this website at techcheck.cengage.com, and that will tell you what's happening. Okay, so if you cannot log on to WebAssign for some reason, you're wondering, is it my computer or is something, something happened to WebAssign? Then go to this website and it will give you that information about, WebAssign is down. We expect it to be back up at a certain time, right? Okay. So, if the Russians start hacking WebAssign, trying to destroy our class, then check that maybe. All right, so let's see. So let's look at these sinusoidal curves. So here we have 4 cosine of 3, cosine 3 of x. So we can describe, right, what's going to happen here. What's the amplitude? 4, right? Yeah. So the amplitude there is the absolute value of 4, which is 4. So that's going to stretch us vertically by a factor of 4, right? So this cosine curve is going to go up to 4 and down to -4 instead of going only up to 1 or only down to -1. Now, the other thing we can compute here is the period. So again, normally the cosine curve repeats every 2 pi units, but how much is this one going to repeat? So take 2 pi and divide that by this coefficient. There it is. So you get 2 pi over 3. So it repeats every 2/3 pi, all right? So instead of taking from 0 to 2 pi to go through the full cycle, this one is going to go through the full cycle in 2/3 of pi. So this one is really oscillating quite a lot more. All right. How much is 2/3 pi approximately? It's going to be a little bit more than 1. Is that something like 1.05 or something? About? No. So 2.1? I'm thinking wrong here. Can y'all do that? So I almost got it right. So 2.1 approximately, right? Okay. It's the period there. How about this one? Before we actually make the graph, let's just write down what we know. So what's the amplitude here? 2, yeah, okay. So this one is doubled in size, but it's been rotated. Since this is the sine curve, instead of going up initially, which is what the sine curve does, right? At 0, the sine curve is increasing, but this one's going to be decreasing. And what's the period then? Well, let's see. We have 2 pi, but this is divided by 1/2. When you divide by 1/2, that's the same as multiplying by 2. Oh, so you have a much longer period here, right? You only go through one full cycle every 4 pi units. So this one's going to be stretched out quite a bit, right? Okay, it's not oscillating nearly as much. Let's take a look at that. See if I can find this example. So there it is, right? There is 4 cosine of 3x, right? So you can see, right, it's really oscillating quite a bit there, right? It's going up and down to -4, and then it's cosine, so it starts at its peak, right? And then is dropping up and then coming up to a peak here. So that's completion of one cycle. And we said that was going to happen at about 2.1, right? Which is 2/3 pi. Yeah, there's where it is. There it is, right? So that's about 2.1. And then the cycle begins to repeat, right? Okay. So it really lots of wiggles in this curve. This one's going to be opposite, however, right? Though here we have stretched the period out. So you see it's not increasing and decreasing. It's not wiggling nearly so much. And because of the minus sign, right, it starts off, and this is the sine curve. It starts off going down, goes down to -2 because the amplitude is 2, right? Then it's going to come back up to 2, and then it's going to go back down again. But notice that's not happening very rapidly. Normally, you would finish a full cycle at 2 pi, which is a little bit more than 6. But now we don't finish our full cycle until 4 pi, which is over here at 12, right? So, so it's not oscillating nearly as much, right, as sine normal. Okay, let's take our break then for a moment here. And we have, what have we not talked about though? So we've got stretches, right? And rotations, but we're missing what? Shifts, right? Okay. We're only going to concentrate now on the, although we've seen some examples for sinusoidal curves, we mostly concentrate on horizontal shifts. All right. So shifting left or right. And for in this context, horizontal shifts are called phase shifts. So we're going to study what's known as the phase shift. But that's just a horizontal shift, right? You can shift up and down, however, but we're not really going to focus on that so much. That's pretty easy to understand, shifts up and down. What's a little bit tricky are shifts left and right. And again, that's referred to as phase shifts. All right, so let's stop there, though, and we'll come back and talk about phase shifts. And do a few more examples like this. Okay, let's resume. All right, so online people, I've been sort of neglecting you guys, but today, but I'm gonna start calling on y'all here in a second. If we get to some examples that we're working on as a class. Okay, so so the last thing that really that we want to mention for sinusoidal curves are what we said before, right? These are horizontal shifts, right? Left or right. So you're aware, right? To shift horizontally, of course, we're going to add or subtract a constant from the x, all right? And so that means that addition or subtraction will happen inside of the sine or cosine function. So it would be inside parentheses here with X, right? So here's kind of the full description of what formulas for sinusoidal curves can look like, right? So for a sine curve, you can have a different amplitude than 1, and then you can have this constant, which the book calls K, which is going to affect the period, right, of the curve. That is a horizontal shrink, and then you can also apply a horizontal shift here, right, by adding or subtracting constant from X, all right? And now you can have a vertical shift, and to do that, you would add or subtract a constant outside of the sine or the cosine function, right? Outside of these parentheses. But again, the book doesn't really focus on these. I don't know if you have any horizontal shifts in your I'm sorry, any vertical shifts in your homework, right? So I just added that on here just to remind you that we can also do vertical shifts by adding or subtracting constants, but not inside of the sine or cosine function. All right, and again, this horizontal shift, right? This is referred to in this setting as a phase shift. All right, so let's look at some sinusoidal curves where we have all sorts of transformations going on. All right, so so this is about as complex as they will get, right? So here we have 3 times the sine of 2 times x minus pi over 4. So we've changed the amplitude, right? We're also going to be changing the period, and then here we have a phase shift as well. So we're going to be shifting this graph left or right. Okay. All right. So let's look at the sort of the parameters here. So our amplitude for this sinusoidal curve is what? 3, right? So we know it's going to go up to 3 and down to -3, right? And then what's the period here? So how do you compute the period? Remember, it's the constant that's multiplied by the x. So it's this constant 2, and then what do you do with that? You divide it into 2 pi. So you get 2 pi divided by 2, which is pi. So that this curve is going to repeat every pi units. This sine curve is going to repeat every pi units instead of every 2 pi units. So it's been shrunk a little bit, right? It's going to be oscillating more than the normal sine curve would. Now, notice in their discussion of the phase shift, they always are writing x minus a constant. All right, they're always writing x minus a constant. So the phase shift here, since here we have x minus pi over 4, the book would say the phase shift here is pi over 4, because we're subtracting the pi over 4 from x. So what effect does that have on the graph, though? So you know how horizontal shifts work. Since we're subtracting here pi over 4 from x, that's going to be shifting it in which direction? To the right, yeah, okay. So that's going to shift it to the right, pi over 4 units. So the whole graph is just going to get picked up and moved pi over 4 units to the right. But remember, it's oscillating quite a bit more frequently than the normal sine curve, right? In fact, it's going twice as fast. It's oscillating twice as fast as the normal sine curve does. So if you had a plus here, you would know that that's a phase shift to the left. The book would say in that case, the phase shift is minus pi over. All right, because they're always thinking of subtracting the constant. So if you have a plus here, instead of a minus, you have to think of this as minus pi over 4, which would be plus pi over 4, right? To get the book's description of the phase shift would be then minus pi over 4. Okay, but that's not what we had. So let's go back to the original problem. All right, so let's make a graph of this then. But again, we already know what to we already kind of know what we're expecting, right? So when we make the graph, we won't be surprised. So I think this is my last example. So let's open that. Is that it? Oh yeah, that is it. Okay, that looked different to me suddenly. All right, so there's the graph. So you can see here, let's pull that over a little bit, right? So what's happened here? What's the amplitude is 3, right? So it's going up to 3 and down to -3, right? What's the period here? It's supposed to be pi, correct? Let's see, how long does it take for this graph to finish one full cycle? So if you start here at 0, right? Okay, and then that would complete one full cycle after it comes up and comes back down again, back to back here to its low point, which is at -3, right? So that that period should be pi, right? Does that look like that's pi? Let's click on this point and see where that point is. Oh yeah, it's at pi. All right. So it tells us very clearly, right? It's starting here at -3, and then it goes up and then goes back down to -3 at pi. So that's a period of pi. And then just repeats that, right? Every pi units to the right and every pi units also to the left. Now, what's a little bit harder to see always is the phase shift, because, you know, when you're shifting sine curves or cosine curves to the left or right, that's hard to see sometimes because, you know, sine curves and cosine curves are periodic, right? They're just, you get copies of the same curve, right? The same piece of the curve over and over again. So the phase shifts sometimes are hard to recognize. But normally, where does sine begin? At 0, right? Okay. But here, where does it hit 0 the first time? Pi over 4, right? Okay. So that means we've shifted that x-intercept, that first x-intercept, we've shifted from 0 over to pi over 4. So that isn't the correct phase shift, right? It's been shifted to the right by pi over 4. So it's really kind of in understanding phase shift, it's really important to remember, oh, sine begins at 0, right? Sine of 0 is 0. Cosine of 0 is what? 1, right? So cosine begins at 1, right? So if you recall, if you remember that, that will help you sometimes to identify from graphs phase shifts correctly. What about this one now then? Before we make the graph, let's see if we can understand what that one looks like. Here, there's a little bit of a trick though, so you have to be careful on this one. Not with the amplitude. The amplitude's pretty obvious, right? What's the amplitude here? 3/4, right? So instead of going up to 1, this one, and down to -1, this one's only going to go up to 3/4 and down to -3/4. So it's not quite as tall as the regular cosine curve, right? But what you have to be careful of here is the change in the period and then the phase shift. Notice that here we have the 2 multiplied into the x, but inside the parentheses, you cannot read the you cannot compare period that way. You have to have the 2 outside of the parentheses here. All right. So that means you're going to have to factor it out of parentheses. You can't factor it in front of the cosine, but you want to factor it outside of the parentheses after the cosine. So let's try doing that. Let's rewrite this one. So we get 3/4 cosine, and then when you factor the 2 out, you would have 2 times what? What's left inside the parentheses here? X plus pi over 3, right? So you have to factor the 2 out of the x, but also out of the 2 pi over 3. So when you factor the 2 from 2 pi over 3, you just get left with pi over 3. Now you can understand the period correctly. What's the period going to be? Yeah, you take 2 pi, right? And do what with it? Divide it by 2. So you get pi again. So that thing is oscillating again more frequently, right? Than the normal cosine curve. And now what's the phase shift here? Be careful. see, this is a plus, but the book always computes the phase shift with a minus here. So in WebAssign, you're going to have to change that to a minus to calculate the phase shift correctly. So how do you make a plus out of minuses there? Yeah, you write minus a negative, right? So you write the plus pi over 3 as minus a minus pi over 3. And then that tells you the phase shift is minus pi over 3. That's just to type the answer in right in WebAssign. What's the phase shift? WebAssign is going to expect minus pi over 3. But you can look and you already know what the effect of this phase shift is going to be, right? If you have x plus pi over 3, what does that do? Shift it in which direction? To the to the left. You got it. Yeah. Shifts it to the left, right? Okay, by pi over 3 units. So this was cosine. Cosine normally starts at 0. Cosine is up at 1, right? Okay, or it's at its high point, which in this case will be right 3/4, right? That's going to get shifted to the left, pi over 3. So it's going to be at its high point at, I'm sorry, it shifts it to the left. So it'll be at its high point at minus pi over, because it shifted to the left. Let's check and see if that's correct. How much is pi over 3 anyway? That's about 1, isn't it? Approximately, a little bit more than 1. Let's graph this and see what it looks like. Is that what we were expecting? I don't know. Let's see. So what's the amplitude here? Supposed to be what? 3/4, right? Well, there's 1. So it should come up to a little bit less than 1. Yeah, that looks right. Up to 3/4 and down to minus 3/4, correct? All right, let's see. What's the period here? Wow, how are we going to read this period? So it starts there at its high point. So where should that be? What should this point be? The y-axis is obviously 3/4. What's the x? We said what? Negative pi over 3, because the high point normally would be at 0, right? On the cosine curve. It would start with a peak right here, but that got shifted to the left by pi over 3 units. So this should be at minus pi over 3. Is he going to read that? Oh, it reads that beautiful. That's right. Okay. So it is minus pi over 3 and 0.75, 3/4. Okay. Just what we were expecting. And then it goes down, comes back up again. And so it completes one cycle. We said that should be pi, right? Is that so there it finishes the cycle at 2 pi over 3. Is that a distance of pi between those two high points there? Yeah, minus pi over 3 to 2 pi over 3. Yeah, that's a distance of pi. Okay, so it completes one period pi units as promised. And then, of course, just replicates that all the way to the right and also all the way to the let me give you a graph here. Let me give you a graph. I'm going to show you a graph. And I've just repeated this. This is the box from above. So this is kind of the full description of sinusoidal curves. Here's a graph of a sinusoidal curve. And there's no phase shift here. All right. So there's no phase shift at all. So there might be changes in amplitude and there might be changes in the period, but there's no phase shift. This is a sine curve. This is a sine curve. Okay. So this is a graph of a sine curve. And I want to see if we can write down the formula for that transformed sine curve. So that's a sinusoidal curve. So let's see if we can write down the formula for this. Just from looking at the graph, we know it's a sine curve. So it's some sort of transformation of the sine function. No phase shift, though. No phase shift. All right. So we don't have to worry about phase shift. So all that's been affected is the amplitude and the period. All right. So let's see if we can figure out what those are. Well, what's the amplitude there? That should be easy to figure out, right? What does it look like it is? Just count it. What is it? See, sine starts at 0, right? And this sinusoidal curve climbs up to what? 4. So the amplitude has to be. Oh, well, that's easy to fill in. Just fill in a 4. It's going up. It's not coming down. So there's no rotation here, right? Because the sine curve begins increasing, right? And now the hard part, though, is what's the, how we change the period, okay? So normally the period of the sine curve is 2 pi, but how much is this one's period? Let's count it. So 1, 2, 3, 4, 5, 6, 7, 8. So now it has a period of exactly 8. So what coefficient should I put in here in front of the x? So in other words, what's the k value going to be in this in the book's description of the sinusoidal curves? They use k as this coefficient that affects the period. So what's our k going to be? Well, let's think about it. Remember, we know the period here, we counted it off. That is 8, right? But how do you calculate that? Normally you do what? You take 2 pi over the k value, right? So if we can solve this equation for k, then we've got it. Can we solve that equation for k? Let's see. Multiply both sides by k, so you would get 8k is equal to 2 pi. And now divide by 8. So how much is k there? It's 2 pi over 8, which is what? Pi over 4? Ah, so there's our k value there. It's pi over 4. Ah, so see, now we can fill that in. We have 4 times the sine of pi over 4 times x. So that must be the formula for that sinusoidal. All right, I'm gonna let y'all try one then. So this again is sine. So see if you can figure out what the new amplitude is instead of 1 and what the new period is there, right? So you can figure out what k value to insert here. Get this graph. Now, one other thing to notice though is normally sine begins increasing, right? But this one is doing what? Yeah, it's decreasing. So that means we've also had what thrown in here? What type of transformation? Anna, so rotation, right? So the amplitude is not going to be positive, or that coefficient that controls the amplitude is not going to be positive. Instead, it's going to be negative, right? So keep that in mind when you write down. Okay, Charles, so try to write down the formula for that one. Just use this as your example. You guys, know me, y'all doing that? See if you can write. I'm going to ask y'all. So see if y'all can write down the formula for that sinusoidal function with a different amplitude and a different period. I'm going to walk around and help the class here. First. Okay. Probably. That's it. That's very good. So what is? How do you? Oh, that was like. So you see the airport. I'm having a problem. Right there, right? 1, 2, 3. Okay, now. Three, three. Right. Three. So starting at 0. That was 0. Down. Up. Back. Just like. Forward. So. False. Yeah. Rotate. Well, interesting. Every time. It's true. But one other little catch. Back. But also notice there's a rotation. Sine begins normally. This one is rotated. How do you count? That's the approach. Sine normally starts up. It's going to start. Set a rotation. Sine will get. Now, yeah, it's just like minus. Perfect. We can see it here. It's very easy to. Oh, that's right. All right. Okay, guys at home, someone at home, you have to, I think the class has got it here. All right, so you got to prove your medal also. I need someone, you can chat it in. I don't know how easy it is to chat. Oh, perfect. Okay, Kenneth. All right, yeah, that's right. So the formula there is y is equal to -3 sine, and this is going to be pi over 2 is going to be this coefficient. That's right. We know it has amplitude of 3 because it's the peak is 3, right? Okay, and the valley is at -3, except this sine curve has been rotated. So normally sine curve, so this is really important to remember. Normally sine curve is increasing at 0. All right, and it goes up and then hits the peak, right, and then comes back down again. But here at 0, the sine curve is falling. Now, of course, we also could have shifted it horizontally, but we didn't shift it horizontally because I told you that there's no phase shift. So that means the only way to get it decreasing at 0 is if there's been a rotation. So this coefficient should be minus instead of plus. Remember, cosine, on the other hand, usually begins at the peak, right, and then is falling to start with, right? Okay, instead of increasing. And now, what about the change in the period? Well, this one now has a period of, instead of 2 pi, right? We can just count this off and see there's a period of 4. But we know to compute the period, we take 2 pi over k, right? K is that coefficient of the x. Then you solve this equation for k. So you end up with what Kenneth got there. K is equal to pi over 2. So that's how you get the multiple there times x. So there's our formula, -3 sine pi over 2 times x. Perfect. Excellent. Okay. All right. So now there's quite a few, as I mentioned, there's quite a few problems on the homework here for this assignment is posted. So take advantage of the graphing tool link that's provided there, right? Okay. Or your graphing calculator. So you're free to use whichever one you prefer. Let me see if I go back here. Here's this homework. So let's open it and see what it looks like. If I can get it to respond. Oh yeah, let me pass that. So that link is in description there. So to see that, you have to open up that description. There's the link to the graphing tool, or you can use your graphing calculator, right? So see, there's a lot of graphs here, right? Where they're just asking you what the graph looks like. So what is this graph going to look like? I think we can figure this one out pretty easily. That's just the cosine curve, but what have we done with it? We've shifted it down 4 units, right? Okay. And so which one of these looks like cosine shifted down 4 units? What? This one? That one's not B. This one's B? Oh, this one? I don't think so. Because remember, cosine, Emil, so this is what I was telling you. Cosine normally, what does the cosine curve look like? It starts at its peak, right? And then it's dropping and then comes back up again. So unless you're shifting left or right or rotating, which we're not here, then it should start at a peak and come down. Which one of those starts at a peak and come down? None of them, right? Okay, except for this one, right? So this has got to be the right one, if any of them are correct. And this one has indeed, has this one been shifted down 4 units? You're looking at that -3 and you're thinking, no, it's only been shifted down 3 units. No, it's 4 because cosine normally begins what? At 1. So it's been, yeah, sine begins at 0, right? But cosine begins at 1. So it's been shifted down to -3. That's a downward shift of, that's right. But you can just plot this on your calculator and see, right, which of these are correct. What's the effect of this one? Just changing what? What is that? Yeah, what's that? What is that coefficient change though? Yeah, the shrinkage or the amplitude is the word. is the correct word. This is changing the amplitude, right? Instead of having amplitude of 1, it's going to have an amplitude of, which is normally what cosine has, right? It has an amplitude of 7/9. So it's only going up 7/9, down 7/9, but it's been rotated. Okay, so which one of these is the cosine curve rotated? This one? I think so, right? Normally it would look like this, right? It would start at a peak and come down, but it's been rotated. So it starts at a valley and is going up. So I think this one is the correct one, right? But again, you can try graphing that and just looking on your graph, right, and see which of those is correct. So there you get an idea of what it's going to consist of. Lots of problems like this. You can go through those pretty quick. Okay, well, I want to give you a chance to work on those. So yeah, what we haven't talked about yet are we have not talked about the other trigonometric graphs. So we have tangent and secant and cosecant and cotangent, right? We haven't mentioned those at all. What do the graphs of those functions look like? We certainly don't use those as frequently as we do sine and cosine, except maybe tangent. All right, so those graphs are probably going to be of less use to us, right? But we do need to have some idea of what they look like. And then we want to look at we have not talked about applications of sinusoidal curves, but that's important because sinusoidal curves are used frequently in applications when you're modeling any sort of quantity that oscillates like this, right? That goes up, comes down, goes up, comes down, and a lot of natural quantities in nature have this property. Okay, they oscillate like this, right? So sinusoidal curves are useful for modeling such quantities. All right. So we do have lots of applications of sinusoidal functions. All right. So we still have a lot to do here with trigonometric functions and their graphs. All right. So we're going to stop there for today, though. So I'm going to turn off the recording, stopping the recording there.